Look up at the night sky, and you're staring into an endless cosmic ocean, one where the smallest pinpricks of light are actually titanic furnaces, burning with unimaginable power. But among these countless stars, some stand apart, defying the limits of what we thought was possible. These are the universe's true heavyweights, celestial monsters so immense and luminous that they rewrite the rules of physics just by existing. Today, we're going on a journey to meet the 30 most powerful stars ever discovered, cosmic giants that dwarf our sun in ways you won't believe. What makes a star powerful? It's not just about size, though that certainly plays a part. Imagine a star so colossal that if it replaced our sun, its surface would stretch beyond the orbit of Jupiter. Now picture that same star unleashing energy so intense that it shines millions of times brighter than our entire solar system combined. That's the kind of raw, unfathomable power we're talking about. Stars that don't just burn, but dominate their corners of the cosmos with terrifying brilliance. Some are so unstable they tear themselves apart in catastrophic explosions, while others defy death itself, bending the fabric of space-time under their gravitational might. This isn't just a list, it's a voyage to the extremes of the universe, where the laws of nature are pushed to their breaking point. From hypergiants with lifetimes shorter than human history to mysterious dark stars lurking in the depths of space, each one of these stellar marvels has a story that will leave you in awe. And by the end, you'll never look at the night sky the same way again. So buckle up, because we're about to explore the most incredible, violent, and breathtakingly powerful stars the cosmos has to offer, where even the brightest lights cast the darkest shadows. If our sun were the size of a marble, UY Scuti would be a skyscraper towering over it, a red supergiant so vast that it defies comprehension. Nestled in the constellation Scutum, this colossal star holds the title of the largest known star in the observable universe, stretching over 1.7 billion kilometers in diameter. To put that into perspective, if you placed UY Scuti at the center of our solar system, its outer layers would swallow Jupiter's orbit and nearly reach Saturn. Just one of its gas plumes could engulf thousands of Earths without breaking a sweat. But size isn't the only thing that makes UY Scuti a cosmic powerhouse. Despite being cooler than our sun, glowing at a deep crimson hue, its sheer volume means it radiates an astonishing amount of energy, outshining our sun by over 300,000 times. That's like comparing a matchstick to a blazing wildfire. Yet, this star's brilliance comes at a cost. Its outer layers are so loosely bound by gravity that they drift into space in massive stellar winds, shedding the equivalent of an Earth's mass every few weeks. Here's the twist: UY Scuti won't live long by stellar standards. Red supergiants like this are ticking time bombs, destined to erupt in a supernova so violent it could outshine entire galaxies for weeks. And when that happens, the explosion might leave behind something even stranger. A black hole swallowing all traces of the giant that once was. But for now, UY Scuti reigns as a true titan of the cosmos, proving that in the universe, size isn't just about scale, it's about raw, unfiltered power. UY Scuti may be a cosmic giant today, but its future holds one of the most violent transformations in the universe. Stars this massive don't fade quietly. They go out in a blaze of glory so colossal it can briefly outshine entire galaxies. When UY Scuti finally exhausts its nuclear fuel, the delicate balance between gravity and radiation that's held it together for millions of years will collapse in an instant. The core, no longer able to resist its own crushing weight, will implode at nearly a quarter the speed of light, triggering a shockwave so powerful it rips the star apart in a supernova explosion visible across interstellar space. The aftermath will be just as spectacular. For weeks, the explosion will flood its corner of the Milky Way with more light than 100 billion suns, scattering heavy elements like gold and uranium across space, the very same materials that someday might form new planets or even life. But what's left behind could be even more fascinating. Depending on how much mass remains, astronomers predict UY Scuti's core might collapse into a neutron star, a sugar cube-sized object so dense a single teaspoon would weigh 1 billion tons, or vanish entirely, leaving behind a black hole where the star once stood. There's still much we don't know. Massive stars like this are rare and unpredictable, with lifespans measured in mere millions of years instead of billions. Some theories suggest UY Scuti might have already shed so much material that its death could be less violent than expected, or it might be hiding unseen companions that could alter its fate entirely. One thing's certain: when this titan finally meets its end, it won't just die. It will rewrite the cosmos around it, proving once again that in the universe, destruction and creation are two sides of the same starry coin. While UY Scuti impresses with sheer scale, VY Canis Majoris takes stellar extremes to another level. A red hypergiant so unstable it's literally tearing itself apart. Located in the constellation Canis Major, this star isn't just large, it's a chaotic, erupting beast, defying everything astronomers thought possible about how stars behave. If placed at the center of our solar system, its turbulent outer layers would stretch beyond Saturn's orbit, swallowing planets like specks of dust. What makes VY Canis Majoris truly extraordinary isn't just its size, it's the star's violent mood swings. Unlike stable stars that burn steadily for eons, this hypergiant experiences colossal eruptions, ejecting massive clouds of gas and dust into space with the force of 1,000 nuclear explosions. In 2007, astronomers observed one such outburst where the star flung out 30 times the mass of Earth in a single event, a tantrum so fierce it left scientists scrambling to update their models. These aren't gentle stellar winds, they're cosmic hurricanes reshaping the star's surroundings into a nebula of its own wreckage. The star's luminosity is equally mind-bending. Despite its cooler surface temperature, VY Canis Majoris shines over 200,000 times brighter than the Sun, thanks to its staggering surface area. But here's the paradox: it's so unstable that traditional physics struggles to explain how it hasn't already self-destructed. The star's gravity can barely hold itself together, and its eruptions create vast plumes of material stretching billions of kilometers, structures so large they've been nicknamed stellar prominences on steroids. Current theories suggest VY Canis Majoris might be in a rare transitional phase, teetering on the brink of becoming an even more exotic object like a yellow hypergiant or a Wolf-Rayet star. Or it could be racing toward a spectacular supernova, one that would temporarily outshine every star in the Milky Way combined. Every observation reveals new surprises, from bizarre magnetic fields to unexpected chemical compositions in its ejected material. One thing's clear: this star doesn't play by the rules. It rewrites them, showing us just how little we truly understand about the universe's most extreme inhabitants. What makes VY Canis Majoris even more baffling is the colossal shroud of dust and gas enveloping it, a cosmic veil so thick it often hides the star from view. This isn't just a wispy cloud, it's a chaotic, ever-changing nebula forged from the star's own violent eruptions, stretching billions of kilometers into space. Imagine a star so unstable it's cloaked in the debris of its own tantrums, like a celestial phoenix perpetually trapped in ashes. These dust clouds aren't just cosmetic, they dramatically alter how we perceive the star's energy. Light struggles to escape through the dense haze, making VY Canis Majoris appear dimmer and redder than it truly is. Yet, hidden behind this curtain, the star's radiation rampages outward, heating the surrounding dust until it glows with infrared light. In fact, if our eyes could see in infrared, this hypergiant would look even brighter than Betelgeuse, outshining most stars in our galaxy. The origin of this dusty chaos is a puzzle. Normally, stars this massive shed material in steady winds, but VY Canis Majoris behaves more like a cosmic volcano, erupting unpredictably and spewing entire planets' worth of dust in sporadic outbursts. Some astronomers suspect it might be caught in a violent phase of stellar evolution, shedding its outer layers in fits and starts as it prepares to transform into a Wolf-Rayet star, a rare, ultra-hot type of star that burns with the intensity of a blowtorch. Others theorize its eruptions could be fueled by hidden companions, with unseen stars or planets stirring up gravitational turbulence deep within its atmosphere. One thing's certain, this star defies categorization. While most red hypergiants fade quietly into obscurity, VY Canis Majoris refuses to go gently, shrouding itself in a spectacle of dust and fury. Every observation peels back another layer of mystery, revealing a stellar rebel that challenges our understanding of how massive stars live, die, and reshape the cosmos around them. Shift your gaze to Orion's shoulder, and you'll lock eyes with Betelgeuse, a star so notorious that its very name sounds like a cosmic warning. This crimson supergiant isn't just one of the brightest stars in our sky. It's a ticking time bomb, closer to exploding than any other star of its size. What makes Betelgeuse extraordinary isn't just its inevitable death throes. It's the fact that we might witness them within our lifetimes. For centuries, Betelgeuse has been a steady beacon in Orion's constellation, but in late 2019, it did something unprecedented. It dimmed dramatically, losing 2/3 of its usual brightness in just months. Telescopes revealed why the star had coughed out a colossal cloud of dust, partially obscuring its light. While Betelgeuse eventually returned to normal, the event sent astronomers into a frenzy. Was this a prelude to a supernova, or just another erratic episode from a star known for its mood swings? If Betelgeuse does explode, the spectacle would be unlike anything witnessed in recorded history. For weeks, it would shine as brightly as a crescent moon, visible even in broad daylight. Nights would be lit by an eerie blue-white glow, casting shadows on the ground. But don't panic, this celestial fireworks show would unfold safely over 600 light-years away. The explosion wouldn't harm Earth, though it might give our satellites a temporary radiation bath. What's left behind could be even more fascinating. Depending on how much mass Betelgeuse has shed, its core might collapse into a neutron star, a city-sized object spinning at dizzying speeds, or vanish into a black hole. Right now, the star's outer layers are a roiling cauldron of convection, cells the size of solar systems, while deep inside, it's likely fusing elements like carbon and oxygen into heavier metals. Every observation peels back another layer of mystery, from strange magnetic fields to bizarre surface hotspots that defy explanation. Here's the twist: Betelgeuse might not go supernova for another 100,000 years, or it could happen tomorrow. That unpredictability is what makes this star so electrifying. It's a reminder that the cosmos doesn't operate on human timescales, and that even the mightiest stars are just transient sparks in the infinite dark. One thing's certain, when Betelgeuse finally does erupt, it won't just be an astronomical event, it'll be a front-row seat to the universe's most dazzling demolition show. Betelgeuse isn't just dimming and brightening at random. Its surface is a roiling, turbulent nightmare that challenges everything we know about how stars behave. Recent observations have revealed bizarre hotspots, colossal patches of intense heat that flare up unpredictably across its crimson surface. These aren't just minor blemishes, some are larger than our entire solar system, glowing far hotter than the surrounding gas. Imagine a star with celestial wildfires raging across its face, and you'll start to grasp the chaos unfolding on Betelgeuse. What's causing these eruptions? One theory points to massive convection currents, stellar versions of lava lamps where plasma the size of Earth's orbit bubbles up from deep within the star, carrying heat to the surface in violent surges. But here's the catch: these hotspots don't behave like anything seen on other red supergiants. Some vanish within months while others linger, distorting the star's shape and even affecting its brightness. In 2020, astronomers using the European Southern Observatory's Very Large Telescope captured something even stranger. Betelgeuse's surface wasn't just uneven, it was pulsating like a colossal heart beating in slow motion. The star's dust veil adds another layer of intrigue. That dramatic dimming event in 2019, it wasn't just fading. Betelgeuse had coughed out a dust cloud so thick it obscured a quarter of its surface. But instead of dispersing, the dust clumped together, creating temporary star spots that mimicked the appearance of cold patches. This wasn't a quiet shedding of material, it was a tantrum, a stellar fever dream playing out on a cosmic scale. And then there's the magnetism. Most red supergiants have weak magnetic fields, but Betelgeuse defies expectations yet again. Measurements suggest localized magnetic loops might be trapping plasma, creating those searing hotspots. It's as if the star has cosmic versions of solar flares, except these are millions of times more powerful, twisting and snapping like rubber bands under impossible strain. The more we learn, the clearer it becomes. Betelgeuse isn't just a star nearing death. It's a laboratory for extreme physics, a place where the rules bend and break in ways we're only beginning to understand. Every new observation peels back another layer, revealing a celestial enigma that refuses to be neatly categorized. Whether it's the churning convection, the rogue magnetism, or the explosive dust ejections, one thing's certain: this star's final act will be anything but predictable. Eta Carinae isn't just a star, it's a cosmic catastrophe waiting to happen. Lurking in the Carinae constellation, this monstrous binary system is one of the most volatile objects in our galaxy, capable of eruptions so violent they've rewritten our understanding of stellar behavior. What sets Eta Carinae apart isn't just its size or brightness, it's the star's sheer unpredictability, a trait it's flaunted for centuries in spectacular fashion. Back in 1843, astronomers witnessed something unprecedented. Eta Carinae suddenly became the second brightest star in the night sky, outshone only by Sirius. This wasn't a gradual brightening, it was an explosion, now known as the Great Eruption, which blasted enough material into space to form 10 suns. The star didn't just shed mass, it tore itself apart, ejecting twin lobes of gas and dust at speeds approaching 2 million miles per hour. Today, those remnants form the Homunculus Nebula, a glowing hourglass-shaped tombstone marking the star's near self-destruction. But here's what makes Eta Carinae truly terrifying. It's not one star, but two locked in a lethal dance. The primary star is a blue hypergiant, a searing, unstable behemoth weighing at least 150 times more than our Sun, with a surface temperature so scorching it glows ultraviolet. Its smaller companion, still 30 times the Sun's mass, orbits close enough that their mutual gravity stirs up apocalyptic stellar winds. When these stars swing near each other every 5.5 years, their colliding winds create shockwaves hot enough to emit X-rays, lighting up like a cosmic flare gun. Energy output: Eta Carinae laughs at ordinary stars. Combined, this duo radiates 5 million times more energy than the Sun, with stellar winds so powerful they carve voids in nearby nebulae. Yet the system is shrouded in its own wreckage, a dusty cocoon that absorbs much of its light, re-emitting it as infrared radiation. If not for this veil, Eta Carinae would outshine every star in the Milky Way except the Sun. Now for the chilling part, astronomers suspect Eta Carinae is primed for an even grander finale, a hypernova. Unlike a typical supernova, which leaves behind a neutron star or black hole, a hypernova would unleash gamma-ray bursts energetic enough to sterilize nearby solar systems. Fortunately, we're safely distant at 7,500 light-years, but if Eta Carinae detonates, the flash could outshine the full moon, casting shadows on Earth for weeks. Whether it explodes tomorrow or in 100,000 years, one thing's certain: when this monster finally goes, it won't just die, it'll rewrite the rules of stellar death. The Homunculus Nebula isn't just debris. It's a celestial masterpiece painted by violence, Stretching nearly a light year across, this glowing hourglass of gas and dust is the aftermath of Eta Carinae's 19th century tantrum, a structure so detailed it looks sculpted. Peer through a telescope and you'll see twin lobes of material expanding outward at hypersonic speeds, their surfaces etched with intricate ridges and valleys like a cosmic fingerprint. These aren't random shapes, they're fossilized shock waves, preserving the exact moment when the star's fury overwhelmed gravity's grip. What makes the homunculus so valuable to astronomers isn't just its beauty, it's a time machine. The nebula's expanding walls contain pristine material from the 1843 eruption, frozen in motion like a stellar crime scene. Spectrographs reveal layers of nitrogen, iron, and even nickel blasted outward, offering clues about the explosion's mechanics. Some elements are traveling faster than others, suggesting multiple eruptions occurred in rapid succession, as if the star exploded, gasped, then exploded again. The nebula also glows with ultraviolet light, energized by Eta Carinae's relentless radiation, creating a fluorescent showcase of physics in action. But here's the real surprise: the homunculus is far from static. High-resolution images taken years apart show its lobes growing visibly, their edges rippling with new knots and filaments. Some regions are cooling into dust, while others stay fiercely ionized, creating a patchwork of temperatures. At the nebula's waist, a dense equatorial disk acts like a cosmic corset, squeezing the outflow into its distinctive hourglass shape. This isn't gentle stellar aging, it's a demolition in slow motion, with the nebula serving as both wreckage and laboratory. Perhaps most astonishing are the whiskers, thin streams of gas stretching far beyond the main lobes. These delicate tendrils, some nearly 6 light-years long, may be relics of even earlier outbursts, proving Eta Carinae's violence isn't new. Recent studies suggest magnetic fields play a surprising role, twisting these jets into helical shapes like stellar DNA. Meanwhile, deep within the nebula's heart, the two stars continue their deadly waltz, their colliding winds carving cavities that glow with X-rays, a reminder that the homunculus isn't just a relic. It's a front-row seat to the next cosmic spectacle whenever Eta Carinae decides to repeat history. Deep in the heart of the Tarantula Nebula, a cosmic monster lurks. R13601, the most massive star ever weighed by science. This isn't just another bright spot in the sky, it's a celestial heavyweight champion, tipping the scales at around 250 times the mass of our Sun. Picture a star so colossal that its very existence pushes the limits of what physics says is possible. If placed in our solar system, R13601 would outshine the Sun by nearly 9 million times, bathing every planet in lethal radiation within moments. But here's what baffles astronomers: stars this massive shouldn't exist. Current theories suggest that around 150 solar masses is the upper limit for stellar formation, as the intense radiation pressure from a newborn star should prevent it from accumulating more material. Yet R13601 laughs in the face of these models, forcing scientists to reconsider how stars are born in the universe's most violent nurseries. Infrared observations reveal this behemoth isn't alone. It's surrounded by siblings nearly as massive, all crammed into a dense cluster within the Tarantula Nebula. This region is a stellar factory operating on overdrive, where gas clouds collapse into giants at a rate unseen anywhere else in the local universe. The star's energy output is equally staggering. Every second, R13601 radiates as much energy as the Sun does in 3 weeks, with surface temperatures exceeding 50,000 degrees Celsius. Its stellar winds howl into space at over 2,000 kilometers per second, carrying away an Earth's worth of mass every few months. Unlike the relatively sedate Sun, this star doesn't gently burn hydrogen, it devours it at a ferocious pace like a cosmic furnace set to maximum. What's truly unsettling is how short-lived R13601 will be. While our sun has shone for billions of years and will last billions more, this hypergiant is already in its death throes at just over 1 million years old. Current models predict it won't go quietly when its core collapses. It could unleash a pair instability supernova, a detonation so violent it leaves no remnant behind, annihilating itself completely in a flash of light visible across the cosmos. Until then, R13601 stands as a defiant challenge to our understanding, proving that the universe still holds mysteries too massive to ignore. R13601 burns so brightly that it's essentially a cosmic candle melting at both ends. Stars like our sun conserve their fuel, fusing hydrogen slowly over billions of years, but this hypergiant operates on an entirely different timescale. With its staggering mass, the core pressures are so extreme that nuclear reactions roar like an unstoppable inferno, consuming its fuel reserves millions of times faster. At just over 1 million years old, R13601 is already middle-aged by its standards, and its remaining lifespan could be shorter than all of human civilization. It's the astrophysical equivalent of a firework, brilliant, breathtaking, and doomed to vanish almost as quickly as it appeared. The star's death won't be quiet. Current models paint a chilling scenario. When its core finally exhausts its nuclear fuel, the collapse won't just trigger a supernova, it might unleash something far rarer and more destructive. At these extreme masses, the star's core could become so hot that photons spontaneously convert into matter-antimatter pairs, creating a runaway reaction known as pair instability. The result, a supernova without a remnant, no neutron star, no black hole, just a titanic explosion that scatters the star's guts across light years of space, seeding future generations of stars with heavy elements like gold and uranium. It's the universe's most spectacular way of saying gone without a trace. Yet even in death, R13601's influence won't fade. The Tarantula Nebula star cluster, already a hotspot of stellar activity, is shaped by this giant's presence. Its ferocious radiation and supersonic stellar winds act like cosmic landscaping tools, carving vast cavities in surrounding gas clouds. These voids aren't empty, they're incubators. Shockwaves from the star's winds compress nearby hydrogen, triggering new star formation in its wake. Some of those infant stars might one day grow as massive as R13601 once did, continuing the cycle of extreme stellar births and explosive deaths. There's also the invisible legacy gravity. The sheer mass of this hypergiant anchors its cluster, its gravitational pull orchestrating the motions of neighboring stars like an unseen conductor. When it finally explodes, that sudden loss could send nearby stars careening into new orbits, altering the cluster's structure for eons. Even the light from its eventual supernova will serve a purpose, flooding nearby nebulae with ultraviolet radiation that illuminates their chemical makeup like a celestial flashbulb. For now, R13601 stands as a boundary pusher in every sense. It defies theories about how massive stars can form, lives with terrifying intensity, and dies in a way that reshapes its corner of the cosmos. But perhaps its greatest lesson is humility, proof that even in our vast universe, there are forces so extreme they bend the rules of physics themselves. Among the universe's most extreme stellar rebels, Wolf-Rayet stars stand apart, cosmic mavericks that strip themselves bare in a frenzied race against time. NWR-102 is one of the rarest of them all. A dying titan so volatile it's literally blowing itself apart. Unlike the bloated red supergiants we've seen earlier, Wolf-Rayet stars like this one are stellar skeletons, having shed their outer layers to reveal searing hot cores that burn with ultraviolet fury. Picture a star so reckless it peels off its own skin, exposing nuclear-fusing muscles to the void. What makes WR102 exceptional isn't just its appearance, it's the speed of its self-destruction. This star's stellar winds roar into space at nearly 3,000 kilometers per second, fast enough to cross Earth's diameter in less than 4 seconds. To put that into perspective, our Sun's solar winds meander at a leisurely 450 kilometers per second. WR102's outflows are like comparing a gentle breeze to a hypercane. These winds aren't just swift, they're dense, carrying away an Earth's worth of mass every few months. Over its short lifetime, this star has likely ejected more material than our entire solar system contains. The composition of those winds is equally bizarre. Spectrographs reveal staggering amounts of carbon, oxygen, and nitrogen elements normally trapped deep in a star's core, now blasted into space like cosmic shrapnel. WR102 isn't just dying, it's performing open-heart surgery on itself, exposing the products of nuclear fusion that would otherwise remain hidden beneath its surface. This makes it a gold mine for astronomers, offering a preview of what stars like Betelgeuse or Eta Carinae might eventually become after their outer layers slough away. But here's the twist: WR102 is vanishingly rare even among Wolf-Rayet stars. Most of its kind are found in tight binaries where a companion star helps strip away their outer layers. WR102, however, appears to be solitary, a lone wolf destroying itself through sheer internal violence. That solitude raises tantalizing questions. Did it once have a companion it devoured? Or is its self-destructive power entirely self-generated? Time is running out for this stellar fugitive. Wolf-Rayet stars typically live less than 1 million years before going supernova, and WR102's furious mass loss suggests it's nearing the end game. When it finally explodes, the lack of surrounding hydrogen, already blown away by its winds, means the supernova could manifest as a rare type IC event, leaving no trace of its original identity. For now, though, WR102 serves as a blazing reminder that in the cosmos, even death can be a spectacle of raw, unbridled transformation. WR102 isn't just dying, it's sprinting toward oblivion at breakneck speed. Every observation of this Wolf-Rayet star reveals telltale signs of a star on the edge, with astronomers detecting fluctuations in its brightness and chemical emissions that scream instability. The star's core, already a cauldron of fused helium and carbon, is likely only months or years away from running out of fuel, not in cosmic terms but in human timescales. When that happens, the collapse won't just be violent, it could rewrite the physics of its corner of the galaxy. What makes this impending doom so fascinating is the star's extreme composition. Unlike typical supernova candidates, WR102 has already blown away its hydrogen envelope, leaving behind a naked core burning heavier elements like oxygen and neon. This exposed core is essentially a stellar pressure cooker, with gravity and radiation locked in a deadly tug of war. Recent spectral analysis shows spikes in silicon and sulfur emissions, elements forged in the star's deepest layers, now bubbling to the surface like a cosmic alarm bell. These aren't just death throes, they're the star's final chemical fingerprint, broadcast into space before the lights go out forever. The collapse itself could be a landmark event. Given WR102's estimated mass somewhere between 20 and 30 times that of our Sun, its core won't just form a neutron star, it's almost certain to implode into a black hole. But here's the twist: this black hole might announce its birth with fireworks. As the core collapses, some models suggest a fraction of the star's material could rebound off the newborn singularity, triggering a gamma-ray burst, a beam of energy so focused and powerful it could outshine entire galaxies for a few seconds. If Earth happens to lie within the beam's path, we don't, thankfully. The radiation would strip our atmosphere bare. For nearby space, the aftermath will be equally transformative. WR102's stellar winds have already carved a cavity around it, but the supernova's shockwave will slam into surrounding gas clouds at 10% light speed, heating them enough to ignite new star formation. Heavy elements forged in the explosion, gold, platinum, uranium, will spray into the void, eventually seeding future planets, Meanwhile, the black hole itself will begin its dark reign, quietly devouring any gas or dust that wanders too close. Some theories even suggest the recoil from an asymmetric explosion could send the black hole careening through the galaxy at hundreds of kilometers per second, a rogue predator set loose in the cosmic wild. Yet the most profound impact might be on science itself. WR-102's death could finally answer long-standing questions about how massive Wolf-Rayet stars die. Does the collapse produce gravitational waves detectable across the universe? Will the black hole's formation emit neutrinos in patterns we've never seen? Every telescope capable of observing the event, from gamma-ray detectors to gravitational wave observatories, will be trained on this spot when it happens. In many ways, WR-102's collapse isn't just an ending. It's a once-in-a-generation chance to witness the universe's most extreme physics in action. And when it goes, it won't just leave behind a black hole. It'll leave us with a masterpiece of destruction, painted in radiation, shockwaves, and the birth of something utterly alien. Hidden in the dusty heart of the Milky Way, the Pistol Star burns with the fury of a cosmic blowtorch, a luminous blue variable so brilliant it defies comprehension. Discovered in the 1990s near our galaxy's core, this star outshines our Sun by over 1 million times, pumping out more energy in 6 seconds than Earth receives in an entire year. If placed at the center of our solar system, its searing ultraviolet radiation would vaporize every planet instantly, reducing them to ionized gas. The Pistol Star doesn't just shine, it annihilates its surroundings with raw, unfiltered power. What makes this star truly exceptional is its location nestled within the quintuplet cluster, a dense stellar nursery just 100 light-years from Sagittarius A, the Milky Way's supermassive black hole. Here, in the galaxy's most chaotic neighborhood, the Pistol Star wages a losing battle against gravity and radiation. Its surface temperature exceeds 30,000 degrees Celsius, so hot that it glows an eerie blue-white, like a welder's arc piercing through interstellar dust. But this brilliance comes at a cost. The star's outer layers are so violently heated that they're blasted into space at speeds surpassing 100 kilometers per second, creating a vast nebula shaped like the weapon it's named after. The Pistol Nebula, a gaseous aftermath stretching 4 light-years across. The star's mass loss is staggering. Every few thousand years, it ejects material equivalent to the Sun's entire mass, enough to seed future generations of stars. These eruptions aren't gentle shedding, they're catastrophic outbursts stripping the star bare in fits of stellar desperation. Spectrographs reveal heavy elements like oxygen and nitrogen in these ejecta building blocks for planets and life, hurled into the void like cosmic graffiti. Yet the Pistol Star's greatest legacy might be its role in galactic ecology. Its relentless winds and radiation sculpt the surrounding gas clouds, compressing nearby hydrogen until it collapses into new stars. Meanwhile, its ultraviolet light ionizes distant nebulae, making them glow like celestial signposts. Some astronomers suspect the Pistol Star's eruptions could even influence the accretion disk of Sagittarius A, feeding the black hole occasional gusts of high-energy material. Time, however, is running out. Luminous blue variables are among the universe's most short-lived stars, and the Pistol Star's extreme mass loss suggests it's racing toward a spectacular demise. When its core finally collapses, the resulting supernova could outshine all other stars in the Milky Way, combined a final flash of brilliance in the galaxy's crowded core. Until then, it stands as a beacon of destruction and creation, proving that even the universe's most violent stars are architects of the cosmic landscape. The Pistol Nebula isn't just debris, it's the star's autobiography written in gas and dust. This sprawling cloud, stretching 4 light-years end to end, holds forensic evidence of the Pistol Star's most violent tantrums, each ripple and filament marking a chapter in its chaotic life. At first glance, the nebula appears as a glowing halo around its creator, but zoom in, and you'll find intricate structures shaped by unimaginable forces. The most striking feature, its namesake pistol shape, wasn't sculpted by gentle winds. It was carved by supersonic eruptions with shockwaves plowing through interstellar material like a cosmic bulldozer. What makes the nebula so revealing are its chemical fingerprints. Spectroscopic analysis shows bizarre concentrations of ionized iron and nitrogen, elements normally buried deep within stars. Their presence here suggests the pistol star didn't just shed its outer layers, it suffered apocalyptic convulsions that dredged up material from near its core. Some regions glow particularly bright in infrared, revealing dense knots where ejected gas cooled into dust grains, each cluster a tombstone for past outbursts. The nebula's structure tells an even wilder story. Near the star, vast bubbles of gas expand outward at speeds exceeding 100 kilometers per second, evidence of continuous hurricane-force stellar winds. But further out, astronomers found concentric shells like rings in a tree trunk, marking separate eruption events. The outermost shell, estimated to be 4,000 years old, contains enough material to form 20 suns, suggesting the pistol star once ejected a staggering chunk of itself in one go. How one theory points to near-critical rotation, the star spinning so fast it flung off entire hemispheres of plasma. Perhaps most astonishing is how the nebula interacts with its brutal environment. So close to the galactic center, it's bombarded by radiation from neighboring stars and gravitational tides from Sagittarius A. Yet against all odds, the Pistol Nebula holds its shape, its structure resisting complete disintegration. This resilience comes from magnetic fields detected threading through the gas like invisible wires, providing scaffolding against the chaos. For astronomers, the nebula isn't just a byproduct, it's a time capsule. By measuring how different elements are distributed, they've reconstructed the Pistol star's life history, revealing periods of relative calm punctuated by cataclysmic shedding. Some even speculate the nebula might contain traces of companion stars consumed long ago, their remains vaporized and scattered by the Pistol star's wrath. As telescopes probe deeper, one truth becomes clear: this nebula isn't just the star's aftermath. It's a warning about how the universe's mightiest stars refuse to fade quietly. They go out screaming, painting their rage across the cosmos for eternity. Mu Cephei isn't just another red supergiant, it's a cosmic jewel burning with the deep crimson glow of a dying ember. Known as the Garnet Star for its rich, ruby-like hue, this stellar giant stands out even among the extravagant residents of the constellation Cepheus. Peer through binoculars on a clear night, and its distinctive color becomes unmistakable, an otherworldly shade of red so intense that 19th century astronomer William Herschel described it as a very fine, deep garnet tint. That color isn't just for show, it's the telltale sign of a star in its twilight years, its outer layers cooled to around 3,700 degrees Celsius as it exhausts its nuclear fuel. Size-wise, Mu Cephei is a true behemoth. If swapped with our Sun, its puffy outer atmosphere would extend beyond the orbit of Jupiter, swallowing Mercury, Venus, Earth, and Mars without breaking a sweat. Its radius measures roughly 1,400 times that of the Sun, so vast that light takes over an hour just to travel from its core to the surface. But what makes this star truly fascinating isn't just its immensity. It's the rhythmic pulsations coursing through its gaseous body like a slow, cosmic heartbeat. Over spans of several years, Mu Cephei expands and contracts by millions of kilometers, its brightness fluctuating unpredictably as internal pressures battle against gravity's pull. Amateur astronomers adore Mu Cephei not just for its striking appearance, but for its accessibility. Shining at around magnitude 4.0, it's visible to the naked eye from dark locations, and its color becomes breathtaking through even modest telescopes. Unlike many distant supergiants, this star feels almost within reach, a dying giant close enough for backyard stargazers to witness its final act. Its variability adds to the appeal. Observers can track its brightness changes over time, contributing valuable data to professional studies. Mu Cephei's fate is written in the stars literally. Spectral analysis reveals it's already fusing helium into carbon deep within its core, a sign it's nearing the end of its life. Within the next million years, a blink in cosmic terms, this garnet wonder will likely detonate as a supernova, briefly outshining the entire Milky Way before collapsing into a dense neutron star. For now, though, it serves as a reminder that even in death, stars can blaze with unparalleled beauty, a garnet set defiantly against the velvet darkness of space. Mu Cephei's crimson glow isn't constant. It pulses like a dying candle flame, its brightness shifting in rhythms that betray the chaos within. Over spans of 2 to 2.5 years, this supergiant swells and shrinks by millions of kilometers, its luminosity varying by nearly a full magnitude. For backyard stargazers, that means the garnet star might shine noticeably brighter one winter, then dim to a deeper ruby hue the next. But these aren't arbitrary flickers. They're vital signs, cosmic EKG readings revealing the star's struggle against its own mortality. Deep inside Mu Cephei's churning core, helium fuses into carbon under unbearable pressure, releasing energy that makes the star's outer layers billow outward. As radiation fights against gravity's grip, the entire star vibrates like a colossal gong, sending shock waves through its tenuous atmosphere. Astronomers classify it as a semi-regular variable. Unlike the clockwork pulsations of Cepheid variables, Mu Cephei's changes follow a looser pattern, with occasional stutters and surges that hint at turbulence beneath its surface. Imagine a pot of water on the verge of boiling, with bubbles forming unpredictably. That's Mu Cephei's interior, scaled up to stellar proportions. What makes these pulsations particularly fascinating is their connection to the star's impending doom. Every expansion leaves Mu Cephei's outer layers more vulnerable, allowing stellar winds to strip away gas at a rate 100 million times faster than our sun's solar wind. Spectrographs reveal trails of silicon monoxide and titanium oxide in these ejections, molecules that form in the star's cooler outer regions, now fleeing into space like embers from a bonfire. This mass loss isn't steady. It comes in waves correlating with the star's brightness peaks. When Mu Cephei swells to its largest size, its gravity weakens just enough to let entire Earth masses of gas escape in violent surges. Yet there's a twist to this rhythm. Infrared observations reveal Mu Cephei's brightness fluctuations don't always match its size changes. Sometimes it grows brighter without expanding, or dims while maintaining its girth. The culprit, enormous star spots, temporary dark patches larger than our solar system that wander across its surface. These aren't like sunspots. They're caused by colossal convection cells rising from the star's depths, carrying cooler material upward in swirling currents that temporarily block its light. For scientists, Mu Cephei's variability is a gold mine. By analyzing its pulsations, they've mapped regions where sound waves travel unusually slowly, hinting at dense layers of partially ionized gas deep within the star. Other anomalies suggest pockets of heavier elements like oxygen sinking toward the core, a process that could accelerate Mu Cephei's demise by choking off nuclear fusion. Each flicker tells a story, whether it's the birth of a new convection cell or the shudder of an internal pressure wave. Even more intriguing is what the star's behavior predicts about its final act. Most red supergiants erupt as supernova, but Mu Cephei's extreme mass loss might leave too little material for a dramatic explosion. Some models suggest it could instead collapse quietly into a black hole, its outer layers already scattered across space. Until then, every pulse, every dimming offers a fleeting glimpse into the heart of a dying giant, a cosmic countdown written in light. VY Cephei isn't just a star, it's a celestial tango performed on the grandest stage. This bizarre binary system features one of the largest known stars in the Milky Way, a red supergiant so vast it would engulf Jupiter's orbit if placed in our solar system. But what makes VY Cephei truly special isn't just its size, it's the star's intimate dance with a smaller, hotter companion, creating one of the most dramatic eclipses ever observed. Every 20 years, the red supergiant slides in front of its blue partner, blocking its light for a staggering 18 months straight. Imagine a sunset that lasts nearly 2 years. That's the kind of cosmic spectacle this system delivers. The primary star is a textbook example of stellar excess. With a diameter around 1,600 times larger than the Sun, it's so bloated that its outer layers are barely held together by gravity, drifting into space in slow-motion plumes. Yet despite its colossal size, the star is surprisingly cool, glowing with a deep orange hue that betrays its advanced age. Its companion, by contrast, is a compact blue star burning at over 20,000 degrees Celsius, a searing counterpoint to the supergiant's fading ember. Together, they form a study in extremes, their gravitational interplay warping both stars into egg-like shapes as they orbit each other every 20.5 years. But the real drama unfolds during their eclipses. As the red giant moves between Earth and its companion, astronomers witness something extraordinary: the smaller star's ultraviolet light, illuminating the supergiant's translucent outer atmosphere like a cosmic flashlight. This backlighting reveals tendrils of gas stretching millions of kilometers into space, structures so fragile they ripple like cobwebs in a stellar breeze. Spectrographs during these events detect heavy elements like titanium and scandium in the supergiant's winds, metals forged in its core now being flushed into space. The system's winds tell another story. The blue star's fierce radiation slams into the supergiant's slower-moving ejector, creating shock waves that heat the gas to X-ray, emitting temperatures. These collisions form intricate patterns resembling interstellar weather systems, complete with swirling fronts and turbulent eddies. Some material even gets caught in a gravitational tug-of-war, forming a bridge of plasma between the two stars, a stellar pipeline feeding fresh hydrogen onto the blue star's surface. Yet for all its grandeur, VY Cephei is doomed. The red supergiant's rapid mass loss means it's shedding the equivalent of an Earth every few weeks, its outer layers destined to form a vast planetary nebula. The blue star, meanwhile, might one day plunge into its partner's swollen envelope, triggering violent eruptions or even merging into a single, unstable object. Until then, this eclipsing giant offers astronomers a front-row seat to stellar evolution's most dramatic acts, a cosmic partnership where size, light, and time itself bend to the whims of gravity. The delicate dance between VY Cephei's two stars isn't just about gravity, it's a cosmic heist in progress. Every orbit, the smaller blue star steals material straight from its bloated companion's outer layers, siphoning gas at rates that would drain Earth's oceans in seconds. This isn't a gentle exchange, it's a violent transfer, with tendrils of plasma stretching across the 6 billion kilometers, separating the stars like a celestial siphon. The blue star's intense radiation boils away the supergiant's loosely bound atmosphere, creating a swirling accretion disk of stolen material that spirals inward at nearly 300 kilometers per second, fast enough to cross the continental United States in under 20 seconds. What makes this theft so consequential is the chemistry involved. As the blue star guzzles hydrogen-rich gas from its partner, it's essentially rejuvenating itself, topping up the fuel it needs to keep burning hot and bright. Meanwhile, the supergiant grows progressively more unstable, its outer layers thinning like a balloon losing air. Infrared telescopes have spotted bizarre anomalies in this stolen material, including unexpected traces of lithium, an element normally destroyed in stellar cores. This suggests the transfer process might be dredging up layers of the red giant that haven't seen daylight in millions of years, exposing primordial ingredients to space. The aftermath of this robbery plays out in X-rays. When the stolen gas crashes onto the blue star's surface at nearly 10% light speed, it heats to millions of degrees, producing flares detectable across the galaxy. Some material misses its mark entirely, instead forming a vast corkscrew-shaped wake that glows in ultraviolet, a celestial breadcrumb trail marking the star's orbital path. Even more fascinating is how this theft alters both stars' fates. Normally, massive stars like the Blue Companion burn out quickly, but this ongoing buffet could extend its lifespan by hundreds of thousands of years. The supergiant, meanwhile, is being stripped of the very material it needs to form a proper supernova explosion. Instead of dying in a blaze of glory, it might collapse directly into a black hole with barely a whimper, its potential fireworks stolen along with its gas. Yet the system's greatest surprise came when radio telescopes detected water vapor molecules swirling in the transfer stream, a shocking find for such a hot environment. This water likely formed where the supergiant's cooler winds meet the blue star's radiation, creating temporary oases in space where oxygen and hydrogen can briefly bond. It's a reminder that even in this hostile, high-stakes duel between stars, the universe finds ways to create the building blocks of life, scattering them across the void with every stolen breath. Antares burns like a furious crimson jewel at the heart of Scorpius, its name literally meaning rival of Mars, for the way its deep red glow mirrors the angry hue of the red planet. But this is no cold, dead world. Antares is a seething red supergiant, a cosmic furnace so vast it would engulf the orbit of Mars if placed at the center of our solar system. Picture a star where the Sun is a mere speck in comparison, with a diameter stretching over 700 times wider and luminosity 60,000 times more intense. Yet despite its staggering size, Antares feels almost familiar in our night sky, glowing steadily as one of the brightest stars visible from Earth, a deceptive calm masking the chaos within. The rivalry between Antares and Mars goes beyond color. Every couple of years, when Mars ventures near Scorpius in its orbit, the two engage in a celestial duel for dominance, their nearly identical hues challenging observers to spot the differences. Ancient astronomers saw this as an omen, a battle between the god of war and the heart of the scorpion. In reality, it's a cosmic coincidence, but one that underscores Antares' regal presence. Unlike distant Betelgeuse, Antares sits relatively close at just 550 light-years away, making it one of the most studied red supergiants in our galactic neighborhood. Peer through a telescope and Antares reveals even stranger secrets. Its outer layers are so loosely bound that they drift into space in slow, shimmering waves, creating a tenuous atmosphere stretching billions of kilometers. Infrared observations show vast plumes of dust swirling around the star, some cooling into solid particles, others heated by its radiation until they glow like embers. Even more bizarre is Antares' companion, a hot blue star orbiting so close that its ultraviolet light excites the supergiant's expelled gas, forming a nebula of fluorescing tendrils around this mismatched pair. Yet the clock is ticking for this scarlet giant. Spectral analysis reveals telltale signs of advanced nuclear fusion, carbon and neon accumulating in its core as the last stages of stellar life take hold. Unlike smaller stars that fade gently into white dwarfs, Antares is doomed to self-destruct in a supernova so powerful it could outshine the full moon for weeks. When that day comes, the blast will seed nearby space with heavy elements, potentially sparking new star formation in its wake. Some models suggest the explosion might leave behind a neutron star spinning at dizzying speeds, its magnetic fields carving intricate patterns into the expanding wreckage. What makes Antares particularly fascinating is its unpredictability. While most stars this massive live fast and die young, Antares has already survived longer than expected, a testament to its slower-than-average burn rate. Some astronomers speculate that past eruptions might have stabilized it, while others point to its turbulent convection currents as a possible lifespan extender. One thing's certain, whether it explodes tomorrow or in 100,000 years, Antares' death will be a spectacle for the ages. A final, defiant flare from the heart of the scorpion before it vanishes forever, leaving only echoes in the cosmic dark. Antares doesn't just glow, it exhales. This crimson giant breathes out stellar winds so powerful they sculpt the space around it into a cosmic masterpiece. Unlike the gentle solar breezes our sun emits, Antares' winds rage at nearly 20 kilometers per second, carrying away the equivalent of Earth's mass every few months. These aren't mere gusts, they're relentless tidal waves of charged particles, tearing through the star's outer layers and injecting chaos into the surrounding nebula. What makes these winds extraordinary is their sheer reach. Infrared telescopes have traced tendrils of expelled gas stretching over 6 light-years, far enough to encase our entire solar system with room to spare. As these winds collide with cooler interstellar material, they create shock waves that heat the gas to millions of degrees, making it glow in X-rays. The result is a vast, fiery halo around Antares, a celestial forge where atoms are smashed together with enough force to produce rare isotopes of aluminum and titanium. But the drama doesn't stop there. Antares' winds carry more than just gas, they're laced with dust grains the size of cigarette smoke particles, forged in the star's cooler outer layers. These microscopic flecks are cosmic time capsules, rich with carbon and silicates that could one day seed planets around newborn stars. Some even clump together into larger structures, forming ghostly filaments that ripple through the nebula like interstellar cobwebs. The winds also expose Antares' deepest secrets. Spectrographs reveal unexpected elements like zirconium and yttrium mixed into the outflow metals normally trapped near the star's core. Their presence suggests Antares' convection currents are dredging up material from astonishing depths, churning its insides like a monstrous blender before spewing them into space. Perhaps most stunning is how these winds interact with Antares' blue companion. The smaller star's intense radiation rams into the supergiant's slower-moving ejector, carving out cavities and triggering secondary shockwaves that glow in ultraviolet. In some regions, the collision zone resembles a celestial weather front, with turbulent eddies and plasma vortices spinning off like interstellar hurricanes. These winds aren't just shaping the nebula, they're sealing Antares' fate. Every atom lost to space is one less available to fuel its eventual supernova. Current estimates suggest the star has already shed 20 solar masses, enough material to form 20 new suns. When the end finally comes, Antares won't just explode, it'll detonate within a pre-carved bubble of its own making, its shockwave ricocheting off walls of previously ejected gas. Until then, its winds keep rewriting the surrounding cosmos, proving that even in its twilight years, this scarlet titan remains a force of nature. While Antares dominates Scorpius with its crimson glow, look northwest to Orion's foot and you'll find Rigel, a blue supergiant so luminous it pierces the night like a diamond. This isn't just another bright star, it's a celestial powerhouse burning 40,000 times brighter than our sun despite lying over 860 light-years away. To put that into perspective, if Rigel replaced our sun, its searing light would vaporize Earth within seconds, turning our planet into a wisp of ionized gas. What makes Rigel extraordinary isn't just its brilliance, it's the sheer violence of its existence. Blue supergiants like this are stellar race cars burning through their fuel at breakneck speeds. Rigel's surface temperature exceeds 12,000 degrees Celsius, nearly twice as hot as the sun, giving it that unmistakable blue-white hue, but this intensity comes at a cost. The star's outer layers are being blasted into space by stellar winds 10 million times stronger than our sun's solar wind, carrying away an Earth's worth of mass every few centuries. Rigel's dominance in Orion's constellation is no accident. It outshines even Betelgeuse despite being nearly twice as far from Earth. Ancient cultures recognized its importance, The name Rigel comes from the Arabic phrase for the foot of the giant, a nod to its position marking Orion's left leg. Modern astronomers, however, see it as a laboratory for extreme physics. Spectral analysis reveals Rigel isn't just one star but a complex system, with at least 3 smaller companions hidden in its glare. The primary star's luminosity is so overwhelming that these dimmer partners were only confirmed in the 21st century, their presence betrayed by subtle gravitational tugs. The star's brilliance also plays a cosmic role far beyond lighting up our night sky. Rigel's ultraviolet radiation ionizes the nearby Witchhead Nebula, a ghostly cloud of gas that glows solely because of this blue giant's relentless energy output. Without Rigel, this nebula would vanish from view, an interstellar sculpture dependent on its sculptor's harsh light. Yet Rigel's fate is already sealed. Stars this massive live fast and die young, and Rigel's furious energy expenditure means it likely has only a few million years left before it exhausts its nuclear fuel. When that happens, it won't just go supernova, it could unleash a gamma-ray burst, one of the universe's most energetic events. For now, though, Rigel stands as a testament to stellar extremes, proving that in the cosmic hierarchy, blue supergiants don't just shine, they reign. Rigel's fate is written in the relentless fury of its own brilliance. Unlike Betelgeuse, a red supergiant nearing collapse, Rigel burns as a blue-white beacon of youth, only about 8 million years old by stellar standards. But don't let its vibrancy fool you. This star is already on borrowed time. Blue supergiants live fast and die spectacularly, and Rigel's staggering mass, around 21 times that of our Sun, means its countdown to destruction is well underway. Where Betelgeuse could explode any day in cosmic terms, Rigel likely has another few million years before its final act. That might sound like a reprieve, but in the universe's grand timeline, it's barely a blink. When Rigel finally exhausts its nuclear fuel, the collapse won't just trigger a supernova, it could unleash one of the most energetic events in the cosmos. While Betelgeuse's explosion will dazzle our night sky, Rigel's demise might be visible even in broad daylight for weeks, outshining every star in the Milky Way combined. The difference lies in their cores. Betelgeuse, as a red supergiant, will leave behind either a neutron star or a black hole, its explosion fueled by the collapse of its iron core. Rigel, however, is massive enough to experience something far more extreme: pair instability. If models are correct, its core could become so hot that photons spontaneously convert into matter-antimatter pairs, triggering a runaway reaction that obliterates the star entirely. No neutron star, no black hole, just a titanic explosion scattering Rigel's guts across light years of space, enriching future generations of stars with precious metals. Distance also plays a crucial role in how we'll experience these explosions. Betelgeuse sits a relatively cozy 640 light-years away, meaning its supernova will be a once-in-human-history spectacle bright enough to read by at midnight. Rigel, at 860 light-years, would still outshine Venus in our sky, but its greater distance tempers its impact. However, there's an unsettling twist. Rigel's axis might not point toward Earth. If its poles align with us when it explodes, the resulting gamma-ray burst could deliver a concentrated beam of radiation powerful enough to strip our ozone layer. Thankfully, current estimates suggest we're safely outside its potential death ray's path. The aftermath will differ dramatically too. Betelgeuse's explosion will leave behind a glowing nebula expanding at thousands of kilometers per second, while Rigel's potential pair instability event could create a nebula rich in rare elements like platinum and gold, celestial alchemy on a staggering scale. Both events will reshape their corners of the galaxy, but Rigel's death throes might fundamentally alter star formation in Orion's molecular clouds, compressing gas into new stellar nurseries. Until then, Rigel remains a brilliant reminder of stellar impermanence, a diamond hanging in Orion's foot, destined to shatter in one of the universe's grandest spectacles. And when it does, the light that reaches Earth will carry echoes of a star that refused to fade quietly, choosing instead to rewrite its corner of the cosmos in a blaze of glory. Deneb blazes as the crown jewel of the summer triangle, a celestial marker so bright it's visible even through the haze of light-polluted cities. This white supergiant isn't just another twinkling dot, it's a stellar lighthouse, beaming from over 2,600 light-years away with the intensity of 200,000 suns. Its brilliance isn't just a quirk of proximity like Sirius or Vega. Deneb earns its place among the night's brightest stars through sheer, raw power, pumping out enough energy every hour to power human civilization for millennia. What makes Deneb truly fascinating is its paradoxical nature. Classified as an Alpha Cygni variable, this star pulses rhythmically like a cosmic metronome, its brightness shifting subtly over days as its outer layers expand and contract. Yet unlike the predictable pulsations of Cepheid variables, Deneb's changes are erratic, sometimes flaring, sometimes dimming, as if the star can't decide how fiercely it wants to burn. This instability hints at the turmoil beneath its gleaming surface, where convection currents the size of solar systems churn plasma like a boiling cauldron. Positioned at the tail of Cygnus the Swan, Deneb anchors one vertex of the summer triangle alongside Vega and Altair, forming an asterism so prominent it's recognized across cultures. Ancient Arab astronomers saw it as the hen's tail in their Great Hen constellation, while Chinese stargazers viewed it as part of the celestial ford, a bridge for celestial lovers. Today, amateur astronomers cherish Deneb as a gateway to deep sky wonders, its light piercing the Milky Way's dust clouds to illuminate distant star clusters and nebulae. But Deneb's luminosity comes at a cost. Spectral analysis reveals its shedding mass at a staggering rate, its stellar winds blowing 1,000,000 times stronger than our sun's solar wind. Every century, this supergiant ejects enough material to build a small planet, shrouding itself in a glowing cocoon of ionized gas. Unlike red supergiants that puff away their outer layers gently, Deneb's winds scream into space at over 100 kilometers per second, carving cavities in nearby interstellar clouds like a cosmic sandblaster. The star's fate is sealed by its own extravagance. Burning through its nuclear fuel at breakneck speed, Deneb likely has only a few million years left before its core collapses. When that happens, its supernova could outshine the full moon for weeks, potentially leaving behind a black hole as its final monument. Until then, Deneb remains a sentinel of the northern sky, a reminder that even the most dazzling stars are fleeting, their light a momentary spark against the infinite dark. Deneb's brilliance masks a cosmic mystery that has puzzled astronomers for decades. How can a star so luminous be so hard to pin down? The debate centers on two fundamental questions: just how far away is Deneb, and exactly how much energy does it truly radiate? Most stars have distances measured with precision, but Deneb defies easy classification, with estimates ranging wildly from 1,500 to 3,000 light-years. That uncertainty ripples through every calculation about its true power, leaving scientists to wonder: is Deneb an extraordinarily massive supergiant, or is it something even rarer, pushing the limits of stellar physics? The challenge begins with parallax, the gold standard for measuring stellar distances. As Earth orbits the Sun, nearby stars appear to shift slightly against the background, allowing precise distance calculations. But Deneb is so far away that its parallax shift is minuscule, lost in the noise of measurement errors. Early satellite measurements from Hipparcos placed it around 2,600 light-years away, while newer data from Gaia suggests it might be closer to 2,200. But even these advanced instruments struggle with stars this distant and bright. The discrepancy isn't just academic. If Deneb is nearer, its luminosity drops from 200,000 suns to a mere 150,000, still staggering, but less universe-defying. Then there's the puzzle of its energy output. Deneb's surface temperature around 8,500 degrees Celsius suggests it's a classic A-type supergiant. Yet its spectrum reveals strange inconsistencies like unexpected dips in hydrogen lines and bizarrely strong helium emissions. Some theorists propose Deneb might be in a brief, turbulent phase of evolution, shedding mass at an accelerated rate as it transitions from a hydrogen-fusing supergiant to something hotter and more unstable. Others speculate it could be a rare, luminous blue variable in disguise, a cousin to stars like Eta Carinae, capable of sudden, violent eruptions. The star's variability adds another wrinkle. Most pulsating stars follow predictable patterns, but Deneb's brightness fluctuates erratically, sometimes dimming by 10% in weeks. One theory suggests these pulsations are driven by subsurface convection zones, gigantic plasma bubbles that rise and collapse like boiling water, distorting the star's surface. Another camp argues magnetic fields are to blame, with star spots the size of solar systems altering its brightness as they rotate into view. What's clear is that Deneb refuses to fit neatly into any stellar category. Its winds, its pulsations, even its chemical composition all hint at processes we're only beginning to understand. Every new observation peels back another layer of mystery, revealing a star that's not just luminous but enigmatic, a cosmic beacon whose full story is still being written in the language of light. The implications stretch beyond Deneb itself. If its distance is greater than currently estimated, our models of stellar evolution might need reworking to account for supergiants burning this brightly. Alternatively, if Deneb is closer but still radiates unprecedented energy, it could represent a previously unknown stage of stellar life, one where stars briefly become cosmic powerhouses before their inevitable collapse. Until astronomers solve this puzzle, Deneb remains a celestial paradox, challenging our assumptions while lighting up the sky with its defiant glow. While Deneb reigns over the northern skies, turn south and you'll encounter Canopus, a stellar titan so luminous it outshines every star except Sirius, bathing the southern hemisphere in an ethereal glow. This isn't just another bright dot, it's a yellow-white supergiant burning with the intensity of 15,000 suns, a beacon so powerful it's visible even when skimming the horizon through Earth's thick atmosphere. Named after the navigator of Menelaus in Greek mythology, Canopus lives up to its legendary status, guiding travelers and spacecraft alike with its unwavering radiance. What makes Canopus extraordinary isn't just its brilliance, it's the star's sheer scale. If placed at the center of our solar system, its surface would extend beyond the orbit of Mercury, swallowing the innermost planets whole. Yet despite its size, Canopus burns relatively cool for a supergiant, its surface temperature around 7,000 degrees Celsius giving it a golden white hue. This paradox, a star simultaneously massive yet temperate, hints at its advanced age. Canopus has exhausted the hydrogen in its core and now fuses heavier elements, causing its outer layers to balloon outward while its core contracts into a ticking time bomb. Navigators have relied on Canopus for millennia, but its role in modern space exploration is even more critical. Unlike most stars used for celestial navigation, Canopus's extreme distance, 310 light-years, means its position appears nearly fixed against the background of closer stars. This stability made it indispensable for early space missions. The Apollo program used Canopus to align spacecraft gyroscopes, while robotic probes like Voyager and Cassini still track it to orient themselves in the void. Even the Hubble Space Telescope locks onto Canopus as a calibration target, its steady light serving as a cosmic lighthouse for humanity's farthest-reaching eyes. The star's influence extends beyond practicality. In cultures from ancient Egypt to Polynesia, Canopus was venerated as a deity or ancestral guide. Maori navigators called it Atutahi, the first light, while Tibetan astronomers saw it as a celestial house for the gods. This universal reverence speaks to its unmistakable presence, a star so bright it transcends borders, etched into humanity's collective imagination. Yet Canopus hides a turbulent secret. Spectroscopic analysis reveals violent winds tearing through its upper atmosphere at speeds approaching 300 kilometers per second, stripping away material equivalent to Earth's mass every few decades. These winds carry traces of barium and zirconium elements normally forged deep in stellar cores, now surfacing in a slow-motion unveiling of the star's inner workings. Some astronomers speculate Canopus might be nearing a transitional phase, preparing to shed its outer layers and emerge as a hotter, more unstable type of supergiant. For now, Canopus remains a steady sentinel of the southern skies, a bridge between ancient wayfinders and interstellar explorers. Its light, traveling across centuries to reach us, carries echoes of a star balancing on the knife's edge, a reminder that even the most dependable giants are, in the end, temporary flames in the cosmic dark. Canopus's golden glow hides chemical fingerprints that defy expectations. Recent spectroscopic studies reveal this supergiant carries an unusually high concentration of heavy elements like barium and lanthanum, metals typically forged in the violent deaths of much older stars. These elements shouldn't exist in such abundance in a star like Canopus, which is still burning helium in its core. The discovery has sent astronomers scrambling for explanations, with some proposing that Canopus might have cannibalized a smaller, metal-rich companion star in its youth. Others suggest it formed from a molecular cloud already seeded with these metals by ancient supernova, making it a cosmic chimera, a star born from the ashes of its predecessors. What sets Canopus apart even more strikingly is its extreme luminosity variability. While most supergiants pulse predictably, Canopus exhibits erratic brightness fluctuations, sometimes dimming by nearly 5% over mere weeks. High-resolution imaging from the European Southern Observatory captured possible culprits, colossal convection cells, each larger than our solar system, churning beneath its surface like boiling golden syrup. These cells transport heat so violently that they temporarily distort the star's outer layers, altering how much light escapes into space. In some regions, pockets of cooler gas sink back inward, creating temporary star spots that further disrupt its glow. The star's wind patterns add another layer of mystery. Unlike the relatively steady outflows from similar supergiants, Canopus's stellar winds erupt in sporadic gusts, ejecting material at speeds varying wildly between 200 and 400 kilometers per second. ALMA radio telescope observations detected bizarre, clumpy structures in these winds, dense knots of gas rich in silicon and titanium that behave more like interstellar hailstones than a smooth stellar breeze. Some astronomers theorize magnetic fields might be corralling these ejections into concentrated streams, though the star's exact magnetic configuration remains elusive. Perhaps most perplexing is Canopus's rotation. Most supergiants spin slowly due to their inflated sizes, but Canopus whirls at an astonishing 100 kilometers per second at its equator, nearly 20 times faster than expected. This breakneck spin flattens the star slightly, making it more oblate than a typical spherical supergiant. One provocative theory suggests the star might have recently merged with a smaller companion, transferring angular momentum like a cosmic topset spinning by a violent collision. Supporting this idea are infrared echoes of what might be a circumstellar debris disk, a ghostly ring of dust that could be the remains of a devoured sibling. These anomalies make Canopus a Rosetta Stone for stellar evolution. Its unusual composition challenges assumptions about how metals are distributed in massive stars, while its turbulent atmosphere offers a preview of what our Sun might experience billions of years from now when it too becomes a red giant. Every new observation peels back another layer of complexity, revealing a star that refuses to conform, a golden enigma whose light carries encrypted messages about the life and death of celestial giants. While the North Pole boasts Polaris as its steady celestial marker, the southern sky has its own guiding light, Sigma Octantis, a faint but unwavering sentinel hovering near the south celestial pole. Unlike its northern counterpart, this unassuming star doesn't dazzle with brightness. At magnitude 5.5, it's barely visible to the naked eye under light-polluted skies. Yet for navigators below the equator, Sigma Octantis is indispensable, a fixed point in the swirling southern heavens, around which all other stars appear to pivot. Its dimness isn't a flaw but a quirk of cosmic geometry. Earth's southern axis simply doesn't point toward any bright stars in this epoch, leaving Sigma Octantis, a modest yellow-white dwarf, to shoulder the responsibility. What Sigma Octantis lacks in luminosity, it makes up for in precision. Positioned less than 1 degree from the true south celestial pole, it's the most accurate southern pole star we have, drifting only slightly due to Earth's axial precession. While Polaris is easier to spot, Sigma Octantis offers navigators a more exact reference point once found. Ancient Polynesian voyagers recognized its steadfast nature, using it alongside the Southern Cross to guide their canoes across the Pacific. Modern astronomers value it too. Telescopes in southern observatories often use Sigma Octantis for precise alignment, its faint glow providing a reliable anchor for calibrating instruments. Finding this elusive star requires patience. Unlike the bold constellations of the north, the area around Sigma Octantis is a sparse void, earning it the nickname the Octant's empty quarter. To locate it, stargazers trace a line from the Southern Cross's longest axis, then follow the curve of the bright stars Alpha and Beta Centauri. Sigma Octantis sits at the end of this celestial roadmap, a humble spark in a sea of darkness. Its faintness actually aids navigation in one unexpected way. When observed through a telescope, its nearly motionless position against the rotating sky creates a mesmerizing effect, like a celestial pivot around which the universe turns. Why hasn't nature given the South a Polaris equivalent? The answer lies in the randomness of stellar distribution. The universe doesn't care about human convenience. Bright stars just happen to fall near our north axis right now. In 12,000 years, Earth's wobble will bring the brilliant Vega close to the North Pole, while the southern sky will gain the luminous star Delta Velorum as its guide. Until then, Sigma Octantis remains the South's quiet champion, proving that significance isn't measured in brightness alone, but in steadfastness, a lesson written in the stars for those willing to look closely enough. Sigma Octantis' faintness isn't just bad luck, it's a cosmic quirk of timing. While Polaris shines brightly as Earth's current North Star, its southern counterpart languishes in relative obscurity because of a simple but fascinating astronomical reality. Earth's axis doesn't point toward any bright stars in the southern celestial sphere right now. It's like spinning a globe and realizing the marker only aligns with a tiny, barely visible dot instead of a glaring spotlight. Polaris, by contrast, happens to be a yellow supergiant 46 times larger and 2,500 times more luminous than our Sun, while Sigma Octantis is a modest main sequence star, only slightly more massive than the Sun and glowing with a fraction of its brilliance. But here's where it gets interesting. Earth's axis isn't fixed. It wobbles like a slowing top over a 26,000-year cycle called axial precession, gradually shifting which stars serve as our celestial poles. 12,000 years ago, the brilliant Vega was Earth's North Star, and in another 12,000 years it will be again. Meanwhile, the southern sky's turn is coming. Right now, Sigma Octantis is the best we've got, but in about 8,000 years, the dazzling blue-white star Delta Velorum will drift within 5 degrees of the south celestial pole. With a luminosity 90 times that of the Sun, it'll outshine Sigma Octantis by a staggering margin, finally giving the southern hemisphere a pole star worthy of Polaris's rival. Why hasn't nature provided a better match in our current epoch? The answer lies in the randomness of stellar distribution. bright stars like Polaris are rare, and their alignment with Earth's poles is pure coincidence. The southern sky just happens to lack a luminous star near its pole right now, a temporary inconvenience in the grand cosmic timeline. Even more intriguing is the possibility that Sigma Octantis might not be alone. Some astronomers speculate it could have an undiscovered binary companion, explaining subtle anomalies in its motion. If true, this hidden partner might one day be revealed, adding another layer to the star's quiet mystery. For now, Sigma Octantis remains a humble guide, a reminder that not all celestial markers need to blaze with glory to serve their purpose. Its faint glow has steered explorers across uncharted oceans and calibrated telescopes probing the depths of space. And when Delta Velorum eventually takes its place, it won't diminish Sigma Octantis' legacy. It'll just prove that even the stars are bound to the slow, inexorable dance of time. Polaris has guided travelers for millennia, not by being the brightest star in the sky, but by occupying a celestial sweet spot, almost perfectly aligned with Earth's North Pole. This makes it appear nearly motionless while other stars wheel around it, a fixed point in the heavens that served as humanity's compass since ancient times. Viking navigators called it Stjärna, the guiding star, while enslaved people fleeing the American South followed it to freedom, singing hymns about the drinking gourd. But Polaris isn't just a static beacon, it's a pulsating Cepheid variable, a star that rhythmically expands and contracts like a cosmic heartbeat. Every 4 days, its brightness fluctuates by about 10% as its outer layers inflate and deflate, heating and cooling in a predictable cycle that astronomers use to measure vast cosmic distances. What makes Polaris particularly special among Cepheids is its proximity, just 430 light-years away, close enough for detailed study. Most pulsating stars of this type are too distant to observe clearly, but Polaris's relative nearness has revealed quirks that challenge textbook models. Its pulsations are slowing down, for instance, a phenomenon first noticed in the 1990s and still not fully explained. Some theories suggest the star might be evolving out of its Cepheid phase, its internal physics shifting as it exhausts nuclear fuel. Others point to subtle interactions with a smaller companion star, whose gravity could be subtly altering Polaris's pulsation rhythm like a hidden conductor slowing an orchestra's tempo. Yet Polaris's reign as the North Star is temporary, an accident of cosmic timing. Earth's axis wobbles over a 26,000-year cycle called precession, gradually shifting which star aligns with the North Pole. 12,000 years ago, the brilliant Vega marked north, and in another 12,000 years it will again. Even now, Polaris isn't perfectly stationary. It traces a tiny circle around the true celestial pole, about 3 times the width of the full moon. By the year 2100, it'll edge even closer, coming within half a degree of perfect alignment before drifting away again as Earth's slow wobble continues. This means future civilizations will need new guideposts, with stars like Gamma Cephei and eventually Vega taking turns as celestial lighthouses. Modern navigation may rely on GPS, but Polaris still holds practical value. Its altitude above the horizon corresponds almost exactly to the observer's latitude, a trick sailors used for centuries to pinpoint their position at sea. Even spacecraft sometimes use it for course alignment, its steady light cutting through the noise of spinning gyroscopes or glitching electronics. Beyond utility, Polaris endures as a cultural touchstone, a reminder that even in an age of satellites and quantum sensors, humanity's oldest astronomical reference still shines with quiet reliability. Its light, traveling 4 centuries to reach us, connects today's stargazers with every explorer, pilgrim, and dreamer who ever looked north and found their way home. Polaris may appear as a solitary beacon in our night sky, but it's actually the brilliant centerpiece of a complex gravitational dance involving 2 hidden companions. The primary star, the one we see shining steadily, is orbited by a close-in sibling called Polaris AB, a yellow dwarf star about 2 billion kilometers away. That's roughly the distance from our Sun to Uranus, but crammed into a system where the stars complete their orbital waltz every 30 years. This companion isn't just along for the ride. Its gravity tugs subtly on Polaris A, causing the primary star to wobble in space like a spinning top with a slight imbalance. Then there's the third member of this celestial family, Polaris B, a far more distant partner circling about 2 trillion kilometers out. Unlike the tight orbit of Polaris AB, this outer companion takes a staggering 40,000 years to complete a single revolution. Through telescopes, Polaris B appears as a faint speck of light, but spectrographic analysis reveals it's actually a hydrogen-fusing star slightly more massive than our Sun. The gravitational influence between these 3 stars creates a delicate equilibrium, with each body subtly affecting the other's movements in ways astronomers are still unraveling. What makes this system particularly fascinating is how these companions influence Polaris's famous pulsations. While the primary star expands and contracts with its 4-day rhythm, Polaris Ab's gravitational nudges appear to modulate these pulsations over decades, like a metronome occasionally sped up or slowed down by an unseen hand. The outer companion's more distant influence may contribute to long-term changes in the system's overall dynamics, though its effects are subtler and harder to detect. Recent observations have added another layer of mystery. Polaris AB shows unexpected chemical peculiarities, an overabundance of certain metals that suggests it might have stolen material from its larger sibling during close encounters. Meanwhile, the primary star's pulsations have been gradually dampening since first measured in the 19th century, possibly due to internal changes influenced by its companion's gravitational tides. This 3-star ballet doesn't just challenge our understanding of stellar dynamics, it offers a rare laboratory for studying how multiple stars evolve together over cosmic time. The system's configuration also hints at a violent past. Most multiple star systems form from the same collapsing gas cloud, but Polaris B orbits in a plane nearly perpendicular to the inner pair, an alignment so unusual it suggests a dramatic gravitational encounter reshaped the system long ago. One theory proposes that a 4th star was once part of this family before being flung into interstellar space, leaving the remaining trio in their current unstable equilibrium. For navigators relying on Polaris's steadfast position, these hidden companions are more than celestial curiosities. They're proof that even our most familiar guides conceal astonishing complexity. The same star that guided ancient mariners across uncharted oceans turns out to be a dynamic system where 3 suns negotiate an intricate gravitational pact, their silent dance continuing unseen behind Polaris's unwavering light. From the unfathomable scale of UY Scuti to the rhythmic pulsations of Mu Cephei, these 30 cosmic titans redefine what it means to be powerful. We've witnessed hypergiants so unstable they shed entire planets' worth of material in weeks, stars like R136, A1 that defy theoretical mass limits, and dying embers like Betelgeuse poised to detonate with the force of 100 million suns. Each one demonstrates the universe's boundless creativity, whether it's Eta Carinae sculpting its own glowing tomb in the Homunculus Nebula, or the Pistol Star blasting its surroundings with winds hot enough to forge rare metals. The diversity is staggering: crimson supergiants that could swallow our solar system, blue-white infernos like Rigel burning themselves out in spectacular fashion, and even humble guideposts like Sigma Octantes proving that significance isn't measured by brightness alone. What unites them all is their ability to shape the cosmos around them. These stars don't just exist, they dominate. They forge heavy elements in their cores, sculpt nebulae with their winds, and upon their deaths, seed entire galaxies with the building blocks of planets and life. Some, like Deneb and Canopus, serve as celestial lighthouses across millennia, while others, like WR102, offer fleeting glimpses into stellar evolution's most violent chapters. Their stories remind us that the night sky isn't just a static painting, It's a dynamic arena where titans clash, evolve, and rewrite the rules of physics itself. Now it's your turn to explore. The next clear night, step outside and trace Orion's belt to Rigel, or find Scorpius's fiery heart in Antares. Even a simple pair of binoculars can reveal VY Cepheus's ruby glow or the subtle pulsations of Polaris. And if you're craving more cosmic wonders, dive deeper, research which of these stars might explode in your lifetime, or hunt down Hubble's breathtaking images of their nebulae. Share your favorite stellar giant in the comments below. Are you drawn to Betelgeuse's impending supernova, or does the Pistol star's lethal brilliance captivate you more? The universe has spent billions of years crafting these masterpieces. All you have to do is